Erik, how are you?
Very good.
Well, let me welcome you to the Beyond Einstein Podcast. Erik is a theoretical physicist from the University of Amsterdam, internationally recognized. I had the great pleasure of working with Erik on a documentary 7 or 8 years ago. I got to spend some time with him and really appreciate his intellect, but also his willingness to think outside of what can be a pretty rigid box in the physics world. But Erik has always been very creative and looking for solutions, and I thought would be an interesting person to talk to.
That's my pleasure. I remember, of course, our collaboration in the other event. I mean, that was also something special, I have to admit, and enjoyed the discussions then too.
Great. Hey, so what is it you're working on right now? What is the problem that you, as a leading theoretical physicist, is trying to solve today?
So we're trying to make progress in understanding the relationship between quantum mechanics and gravitational forces, and we have made some progress. And certainly in understanding objects like black holes or certain space-times, we have already a pretty good understanding of how to describe space-time and black holes at sort of at a microscopic level in terms of quantum mechanics. But we're trying to make progress to describing also the real universe out there, where we have mysterious phenomena happening associated to dark energy and dark matter. I mean, that's also in describing the early universe, but also our present universe. The big questions that we don't understand yet, and we're trying to make progress there.
One of the things that fascinated me when we met years ago, you were working on math, trying to remove dark matter. I believe remove dark matter from the equation, saying we can explain our observations without having to use dark matter. Are you still working on that?
Yes, and the ideas I had then are still in place, and the goal is to indeed develop a theoretical framework. You can think outside of the box, but eventually you have to convince your colleagues and other people so that they accept what you have discovered. Otherwise, the ideas might even disappear. So I'm certainly working very closely together with many of my colleagues and trying to sort of get them into that direction. Because for a long time, people kind of avoided addressing some of those questions, like, do we really understand how the gravitational force works at cosmological scales? And how do we incorporate things like dark energy and the fact that the universe appears to be expanding in our microscopic understanding of what space-time is and how gravity emerges? I mean, one of the main things that has happened in my field is that many more people, and especially younger people, are accepting the idea that we should think about the gravitational force as being emergent from something more microscopic. So this theory of emergent gravity that I also developed and used to describe these dark matter phenomena is gaining indeed attention, and also, people that believe in this and also are working on that.
So when you say emergent, what is it emerging from?
I mean, there's kind of an abstract notion that we also use in writing down models for quantum computers and so on, that we call the quantum information. And at the microscopic level, this is also what the world sort of is made of. And you have to draw an analogy, I think, with other emergent phenomena, like what we know in thermodynamics, where we also have laws that appear at the macroscopic scale. I mean, when we look at the temperature and the pressure and of a gas, they are derived from something microscopic that, we now call molecules and atoms and so on, and we have some idea what it's made of. So we have to do something similar for space-time. And there, I think the knowledge of what it really is, I mean, it's not particles, it's something that makes up black holes. I mean, really at the microscopic level, where it's not just particles, but something that we can describe in this language of quantum information. The other ingredient that goes in there is this idea of quantum entanglement, which is something that appears when you think about quantum mechanics. It's something that Einstein sort of was very confused about, and he talked about spooky action at a distance. But it's something that people now understand is essential for describing quantum information, and also we have now understood that we indeed can relate this to the concept of gravitational of gravity. So there is, as I said, a full a large group of people working on this connection between quantum entanglement and quantum information, and then gravity on the other side in space-time. So this field has been developing, and I'm helping to sort of develop it further, but also push it in the direction of answering questions about, well, the cosmos and in particular dark energy and dark matter.
Yeah, one of the things that has always bothered me about from a layperson's perspective about physics, at foundational physics, is that your idea of emergent. What is it emerging from? And one thing that really bothered me for a long time is the use and the dependence on fundamental forces in the base model. Both quantum and relativity are dependent upon things that have no power source. They just happen because they happen. Are you comfortable with the fundamental forces being foundational in our physics?
Well, it's something that was very successful in developing the theories that I think, that we have now, but also are kind of belonging to what I call the 20th century. We're already in the 21st century for quite some time now, and we indeed are developing a new language. So the idea in the last century was indeed that you have to start from elementary particles and from fundamental forces, and you basically have to assume their existence, but that's nothing that you could derive this from. And now I think we moved further, and we are indeed thinking about something even more microscopic, from which these concepts like forces and particles and also space-time itself are then derived. So the notion of space-time is something that we use also in our description of physics, but where does it come from and what is its microscopic structure? That's exactly the kind of questions that we are now trying to address. For instance, how many dimensions do we have? What is time in this context? So emergent space, but also emergent time are central notions of what we're now trying to kind of develop in the language of physics that I think is new to people that think about forces and particles, because we're really using very different concepts.
So that at some point, hopefully in the 21st century, the idea of fundamental forces will be explained through a different language and sort of removed from the theoretical foundation.
That's indeed my belief, and I think we have already seen some examples of this. I mean, one of the main ingredients that, and even indications that something special is happening with the gravitational force comes from the study of black holes. And there we have to go back to what Hawking discovered in terms of, that if you combine it with quantum mechanics, black holes do radiate, they have a temperature, and they have even something called an entropy, which we now can interpret as sort of a measure of the amount of information that's inside a black hole. And it's also connected to this notion of entanglement. But what was more surprising is that actually the equations that Hawking and his colleagues like Bekenstein derived look like these laws of thermodynamics, the same laws that we know are emergent from molecules, but in this case it's not clear what they emerged from. And now we have a better understanding. I mean, it's this, as I said, this notion of quantum entanglement, and there's also laws when, like the first laws of thermodynamics, can also be applied to entanglement, and then suddenly the equations that Einstein wrote down for the gravitational force, they kind of drop out from the considerations that also derive the laws of thermodynamics. So we have sort of a statistical explanation of what the gravitational force comes from, and this is a new development, and I think it actually even progressed quite a bit since the last time we talked. I mean, if you look at the literature, even just the mainstream literature, many papers have been written about this. And in that sense, I think the ideas that I put forward more than 10 years ago have already descended into the main developments, and I think are no longer seen as being outside of the mainstream. My ideas about dark matter, though, have not been sort of generally accepted yet, because there people have, as I said, haven't even thought about, even began to think about these questions yet. And this is sort of changing slowly. There's something happening there that we need to understand, but also need to develop a theory for. Same kind of happened a bit with quantum mechanics. I mean, Einstein already mentioned didn't fully accept all the ingredients of quantum mechanics, but nowadays it's such an important part of physics, and we're developing indeed all these tools like quantum computers and so on. This is takes centuries. I mean, even what Einstein wrote down, his theory of gravitation was well slowly accepted, but eventually also confirmed by things like gravitational waves. But also that took a century. So the time scales in physics are not short. I mean, they're long, and that happened for quantum mechanics, and surely now for quantum gravity. We have already been thinking about it for 40 years or something, or more than that. And I think we're getting closer, but it's still some years away, and maybe even another decade or so.
Very difficult for the industry to admit that a direction that they were in is wrong. Like it's, the progress made in the, the super colliders over the last 50 years have been relatively small, nothing substantial. At what point do you raise a white flag and say, okay, maybe that's not the right direction for us to be researching?
Well, I mean, a very important part of this is also the experiments that are being done. I mean, we as you remember, we also talked to Helena April, who was leading this big experiment, and they are searching for these sort of dark matter particles, also because they're told by other theorists that they should be there, but when they don't find it anymore, of course, they get well, disappointed, but also theorists learn from that and they will adjust their ideas. But for this new approach, where we kind of think about gravity in a different way, I think there we really need to sort of get to a formulation of the theory that, well, is working in a consistent and logical way, and that makes theorists convinced that it's the right direction. Usually necessary for any theoretical development is that there's some phenomena that we haven't seen that we can predict, and then somehow we discover this. I mean, this is where indeed this dark matter issue is a bit difficult to sort of get people to give up on, because they have so many dark matter models that it's always possible to match the data. I mean, you can always tune your parameters so that the data come out, and this is kind of the game they're playing. Having a very beautiful sort of new theory that explains the origin of gravity in space-time, and then people may also start become convinced. But this, as I said, is something that may take decades, and perhaps what you already mentioned may take other people sort of to disappear from the field. Indeed, invested so much time in their old theories that for them it's very hard to admit that they have been spending their energy and their whole career on the wrong idea.
Yeah, that is one of the problems with the evolution of physics, is the rollover. You theorists give the roadmap to researchers, and the researchers then go off and try to prove or disprove whatever you're proposing. Are there experiments that you're looking at doing that can help advance this process?
I have one other direction that I worked on with a colleague from Caltech that has to do with thinking indeed about observable effects coming from quantum gravity, and that eventually became a collaboration that we called Curios. It's sort of observational signatures for quantum gravity, and in particular also related indeed to entanglement. I mean, we have been working on a microscopic description of space-time in kind of a model universe. I mean, one of the ingredients in the equations of Einstein is something called the cosmological constant. It's a constant that Einstein added to describe some energy that's in space-time. And this energy can be positive. And actually in our universe, that's quite an important ingredient. It's called dark energy because it also leads to a change in the space-time because it's expanding. The space-time is, well, as we know, the universe expands. We see things moving away from us, and the speed at which this happens can only be explained if there's some part of the energy in the universe in the so-called dark. But the models that people have now understand they don't have that dark energy in them. So we have some way have to incorporate this dark energy in our current description. The other thing that we observe is some strange behavior of how galaxies and other objects are moving at very large distances, at cosmological scales. And in order to explain that, people have to add something called dark matter. That's something else than dark energy. It's some form of what they say matter, like particles, but we cannot see it. I mean, it's something that creates a gravitational force, and it also makes galaxies rotate faster because there's more gravity inside. And this is indeed what being observed, and it's being explained by adding more matter in the galaxy than we can actually see. And this, many people believe, is indeed some particle that also existed in the early universe and plays a role in how even these galaxies were formed. Now, if gravity works differently in the cosmological distances, like I believe, then we can also explain the same phenomena in a different way without assuming particles or anything that looks like dark matter. It's simply an additional part of the gravitational force that is stronger than that we normally think it would be, and that also would explain all these observations and also the way that galaxies then are formed. So this is kind of where I'm trying to get to, is that I want to have a description of the universe and the cosmos without dark matter, but where the gravitational force emerges in a way that indeed is different than what Einstein would have written down. So there is a change in the equations because of its emergent behavior. And that is something that we can indeed try to test, because there's some way that description also gives predictions that we want to then, test with observations.
And do you think in our lifetimes that they'll find something that allows you to make this mainstream and supplant some of the existing theories? Can we get there?
I think the hope I have is really on the theoretical side. And what I hope is that the theory develops in the next decade or 15 years in such a way that indeed it kind of answers questions about the origin of the gravitational force. I mean, it will be a slow change in opinion. And as you already said, I mean, this is something that may not be accepted by everyone. I do think that this can happen in I would say 10, 15 years.
One thing that attracted me to what you were doing is applied logic. The idea that because the observation showed something unusual happening with gravity on the large scale, that the entire construct of the universe changed with the addition of dark matter, to me made absolutely no sense whatsoever. And so your effort to go in within the framework of our existing paradigm and try to explain those observations without dark matter made a lot of sense to me, because I know Elaine has been working on this for quite a while, and a lot of other people have. And if there's that much more dark matter out there, you'd think we'd find something at some point.
That has been kind of the consensus. And when I started out in physics, I mean, that's when sort of that idea started appearing that there should be dark matter. And I personally accepted it for that time, but I felt something uncomfortable also about cosmology in general. As a theorist, or even as someone thinking about what gravity is, I mean, you think there are other possibilities. I mean, when something doesn't work with the observations, you always have to check what are the possible things that could be wrong in our theoretical framework.
There should be a point of, oops, the theory's wrong. We need to go back and find out why it's wrong. And the work that's been done in the particle physics and the work that's been done in the xenon-like labs and all of that have given us enough data to say this may not be the right direction. But with a construct of how peer review process and how our physics institutions work, that's a really hard thing to do.
It is a hard thing to do, but also because we have, there are many ideas that people will try it, of course, but they will change directions a little bit, but they don't change the full theory of gravity, which is not an easy thing to do. That also partly is because Einstein's theory, in a certain sense, is very convincing, and there's certain beauty to it that people try to sort of not give up on. And also the stature of someone like Einstein, I mean, sort of makes people think that he's always right. And this is where indeed some more major thing needs to happen to convince people that there's something wrong with his theory. And I think this idea of emergent gravity, there you can sort of see why things are can change, because you have to derive then Einstein's equations from something that's more microscopic, and then you can always go back to what do I need to assume to get to Einstein's equations. That's kind of how I try to work, and there are certain assumptions you need to make. And then you can ask the question, well, if those assumptions are not valid, I mean, what will change? And then you find that you can then use the same theory to derive different equations. And this is kind of what the direction is I want to go into, is that there is indeed new phenomena happening, or even microscopically, when we describe this universe with dark energy.
When you say microscopic, is it possible that the emergent gravity is emerging from a field that doesn't actually have a physical presence yet? That it's a flow of something that emerges into gravity?
And this is where one thing I learned is that physics and even humans, I mean, they generally, we use kind of language that we can sort of relate to or even visualize. But if you really think about what space-time is at a microscopic level, nature doesn't look the same at all scales. I mean, when we go very tiny scales, we have these particles and quantum mechanics and so on, and many things look differently. And in a certain way, we're zooming in even further, and then we can find things that are not describable by what I would call our classical intuition, our human sort of everyday life intuition, which is not applicable maybe in the microscopic description of space-time. So microscopic for me really means something that is quite abstract in terms of even its math, in the sense that when you don't assume space-time, you have to derive it from something. And here we are making progress. I mean, you have some language there, which is coming from quantum mechanics, some mathematics that we can apply that leads to space-time and the notions of it in quite a beautiful way. I mean, that's one of the things I've been working on for the last 5 years or so. We have ways of describing emergent of space-time from this microscopic language.
Is it, we're talking about the possibility that Einstein's gravitational theory was incomplete or not fully understood at the time of the space-time. Is it possible that Einstein's error was something that was an omission, a level of?
No, I don't think so. I mean, in a way, I mean, when Einstein wrote down his equations, he didn't say that Newton was wrong. I mean, Newton wrote down a law that works perfectly well in many circumstances. And in that sense, Einstein was not wrong. What Einstein did, he showed there are situations where Newton's laws start to sort of break down, and that you need to take into account, in his case, what is the speed of light. And what I'm saying is that Einstein's equation somehow at these large scales, when the size of the universe becomes sort of important, may break down. So it's more like there's certain circumstances where his theory doesn't completely work. It doesn't mean that his theory is wrong, because there's some very precise limits in situations where it does work. There are many other predictions, like the existence of black holes and so on, that can be verified. And so certainly Einstein's theory is not completely wrong, but we kind of go to the next theory, which sort of explains where Einstein's theory comes from, and also shows where his theory might be, has to be modified, or at least be corrected. And therefore, it's not like I'm taking his equations and slightly change them in some tiny place. I mean, it's really a fully new theory that was not something that Einstein could have thought about, even because in his time, the language that we are using now and are developing now wasn't even present at that time. So it was not a simple mathematical mistake or something like that. It's really a totally new view that we are developing at this moment.
You identified the problem that you're trying to solve is basically the unification of physics, to try to tie quantum in with relativity,
Yes.
to complete Einstein's work, and which I believe is one of the two very large mistakes, or the illogical mistakes that are in today's foundational physics. The other is the need for the replacement of fundamental forces as foundational theories. And so what we've focused on is, how do you remove fundamental forces? And the conclusion was, and it came through a very unusual path, was that if you extend the definition of energy to include a non-physical energy or an ether, as Einstein told us back in 1920, probably needed, and you define the properties of that non-physical energy, that would go a long way to describing it's from that field that emerges gravity. And it's from that field that provides the energy that allows the subatomic world to operate. And with that, you can remove fundamental forces, and you can mathematically tie a theory that starts at the atom and goes up to the orbital gravities of galactic disks. Extend E equals mc squared to have the space-time relationship. And I think you can come up with a pretty clean, simple model that helps converge with your convergent
Well,
theories.
I understand what you're saying, and it may very well be that we have some description that kind of goes along the line that you mentioned. I think the theory side of it, we are developing some new language that doesn't even, as I said, use fields, but sometimes when you have an idea and has been developed, you can kind of describe it effectively in terms of this field language. And then indeed, there might be an additional part of the energy that we should sort of distribute over the space-time like a field. One of the ideas that people have tried also in even explaining certain cosmological phenomena is called dynamical dark energy, where indeed things change more locally and in ways that normally dark energy doesn't do. My goal, at least, is to really develop a new theory based on concepts like quantum mechanics and quantum entanglement. As you say, the forces, we want to understand how they emerge. This is something that I think is first needs to be done, I think, for the gravitational force, because I think that is where it's most urgent and also most obvious that it's an emergent force. In the cosmos, the gravitational force is the most important force. The other forces, they become important in accelerator experiments or in describing how matter kind of is formed from molecules and so on. But the structure of space-time, certainly at large distances, is mostly well described by gravitational equations. And that's where I think the emergence kind of has its most important consequences.
Yeah, I think that we looked at it differently. We looked at it from the bottom up, because the places where you observe gravity are simply around places where there are large accumulations of matter, of atoms. And so if you could figure out what's going on at the subatomic level that requires the movement of energy to an emergence of what can ultimately become gravity, then you can scale that outward. So we're sort of looking at it from a different direction than you are, and hopefully can end up in maybe the same spot at some point of, energy converging, non-physical energy converging on large objects. And as you have the distance, it's basically the inverse squared law reversed. The energy concentration gets greater and greater until it reaches a level where you get a gravitational attraction on other objects it's passing through. And that's driven by the energy needs of each atom. Each atom has to have an energy source. You can't make an you can't make an electromagnetic field. You can't have an active, solid plasma field around a nuclei unless there's some type of, in our logic, some type of an energy source. And that energy source is the ether. Extend definition of energy to include a non-physical state. Put it back in, define a relationship with that energy to matter, like a nuclei is like the flame of a candle. It's sucking in oxygen. The nuclei is sucking in this energy. And then you cumulatively grow it, and then you end up with what we observe as the local gravitational effects. And then you also have flows around larger objects too, but it's just a different way of looking at the relationship between the atom and larger objects.
I think I need to read more in order to fully understand what the idea is, and see how it could be related to my work. I also developed a description based on the microscopic understanding that uses an analogy with elastic energy and so on, where you can also, I mean, kind of what you mentioned in terms of this ether, where there's something that behaves like an elastic force that kind of is the way we can also describe that additional force coming from the dark energy. So the dark energy indeed behaves then more like a medium that reacts to the presence of matter. And that description actually sounds somewhat like what you're describing, in the sense that there's indeed, as you say, when we have matter localized, there's more and more, well, a certain region of space where this energy is present and actually being affected also by the matter particles. And then the way that the gravitational force acts is then because of the way that this medium also back reacts to the presence of matter. And I call this a kind of the additional dark component of the gravitational force. And that would be then the alternative to having dark matter there. I mean, in the sense that there's then an additional component in the gravitational force that is related to the presence of this, let's call it a dark energy medium.
Yeah, again, language is very difficult, but we're calling it ether energy or clear energy. And it makes everything very, very simple if you add it in there. Now, is it complete? I don't know. Can you scale it mathematically? I believe you can. We've done it through the solar system, but not as many variables as you need to have. But you can explain planetary orbits and why everything's on the same plane, going the same direction, all that. But I'd love to have you look at it, Erik. And
I can do that. Yes.
We're trying to solve the same problem from different directions. Yeah, I think that when we come up with the right solution, it's going to be simple and it's going to be elegant. It's going to be clean, and I think it'll be something we can understand. It'll be very different, as you've said before. It'll be very different than what we have today. It'll transcend what we have today, most likely. It is being built off of Einstein's work. I'm hopeful we can get there, and I'd sure like to understand it. And I've read some of your work talking about, there's a chance we won't find it, and be curious as to how you think about that.
Well, I do think that it requires an effort by many people, and here I do think that the fact that there's a community of physicists out there that are trained also in the mathematics and are also familiar with the problems that we already know how to solve, and sort of want to move in the other direction. I think we're living in an exciting time where we are developing a new theory of the gravitational force and of space-time, and combining it with quantum mechanics. So you might call this a unified description. I mean, the thing I'm excited about is also that there's plenty of young people that are still excited about these questions, and they are indeed collaborating with me and with colleagues thinking about similar questions. The more likely outcome that it will be a theory that's developed by many people and whose name we may not yet known, and so there's hope, at least I think, that we will find it in the next 10, 15 years. And that maybe already we're at the moment that we can accept that there is this new theory and that there's different explanations for, these phenomena associated to dark matter.
Well, I wish you'd hurry up. I'm not sure I can make it much longer than 15 years. So you got to really get on it. I'd like to see it happen.
We were trying to make progress. I mean, it's a bit of a tragedy for every physicist that we won't know what's the final, the new ideas that are coming later. We're actually in a very good period where more people are thinking about it, and also younger people. So progress might also happen more quickly. I mean, one of the things that we experience in science is sometimes big breakthroughs, kind of moments when really something special happens. They don't come very often, and they always also sometimes difficult to predict. So maybe we should hope for one of those breakthroughs, and then the answer comes more quickly.
That would be nice. Thank you very much, Erik. It's great to see you again, and hopefully we can cross paths in the real world sometime in the next couple months.
All right.
Okay.
Thank you.
Thanks, everybody.